Section 13.6, the binomial theorem and probability. We're going to start with a vocabulary term here. It's binomial experiment. The reason we relate this back to the binomial theorem is because we do use the binomial theorem in part of the formula for probability with binomial experiments. I'm not going to focus on that because, like we said, it kind of relates back to combinations. It relates back to Pascal's triangle. So I'm not going to focus mainly on the binomial theorem, but that's kind of how this is all kind of interrelated. So a binomial experiment is an experiment with the following conditions. There are n independent trials, so one trial does not affect the other. Each trial has exactly two outcomes, or we can group them into two separate outcomes, either success or failure, and then the probability of success is the same for each trial. So we're rolling a six-sided dice a certain number of times, or we're guessing on a multiple choice question where one guess on one question doesn't affect the other questions, something like that. Okay. The formula for binomial probability, if we're looking for the probability that we have k successes, so we're gonna guess on 10 multiple choice questions and the probability that we get 3 correct, how we would do that. The formula for this, you can see down here, I've got a lot of variables, n, k, r, p, and q. And we do have a lot of variables, but if we can identify what is what, really it's just a matter of plugging and chugging into a formula. So the probability of k successes is equal to nck, so that's where the binomial theorem comes in, because remember the binomial theorem gave us the combinations, the number of combinations, which is also the number on the Pascal's triangle, so that's going to be where the binomial theorem comes back, but we're not going to focus on that. We're going to just focus on the formula. We start with nck, so the number of trials, we want to choose a certain number of them to be successful, times p to the k power times q to the r power. Now, the k and the r, and even the p and the q, these four variables, well, specifically p, q, and r, those are kind of arbitrary. Those are the variables that I learned growing up. So those are the kind of the variables that I like to use. To me, those are the ones I've learned, and those are the ones I'm most comfortable with. But if you want to come up with a different set of variables, I mean, by all means, go ahead. But these are the ones I'm going to use. So again, n represents the number of trials. We said that up here at the beginning. The k, just like we said, k successes. Okay, so n choose k. We need to decide which of the n are going to be successful. P is the probability of success. Okay, so if we're guessing on a multiple choice question, so A, B, C, D, then the probability of success would be 0.25 or 25%. Q then is the probability of failure. Okay, so if it's 0.25 of success, then 0.75 would be the probability of failure. And that might be something to note as well. Probability of success plus the probability of failure, P plus Q, needs to be equal to 1. Okay, those are the two outcomes, success and failure. And remember, probabilities add up to 1. They can be no more than 1. And then R is the number of failures. So if we're going to look for 3 correct out of 10 questions, then the R value, if we're getting 3 right, that means we're getting 7 wrong. So that might be something else to write down on the side. The number of successes, K, plus the number of failures, R, that must be equal to your N, the total number of trials that you are performing. So we're going to be using this formula right here a lot in this video. So we're just going to try to get more comfortable with it, identifying which variables are what, or which value represents which variable. And we're going to kind of just try to kind of work it down from there. So I got 3 examples here for you. This one's probably the shortest of the 3. The next one is going to be the longest of the 3, and then the last one will be kind of in between. So 8 out of every 10 persons who contract a certain viral infection will recover. If a group of 7 people become infected, what is the probability that exactly 3 people survive? So we have a lot of information here being thrown at us. I think this one right here, the group of 7 people, that is going to be our N value, because that's our test group. That's our number of trials. So we can say that N is equal to 7. Now this 8 out of every 10 persons who recover, that's going to be our probability of failure, or not a probability of failure, a probability of success, because success would be surviving this virus. So we can say that our P value is going to be 8 out of every 10, which is 0.8. And if the probability of success is 0.8, then we could probably say that our probability of failure is going to be 0.2, because remember, successes plus the failures, the probability of success plus the probability of failures is going to equal 1, and 0.8 plus 0.2 is 1. Now, the last piece of information that we're given is exactly 3 people survive. That's what we're asking for. That's what we're looking for. So that means that our K value, because remember, success is surviving, makes sense. The k value here is going to be 3. And if we're looking at a k value of 3, that means the r value here, remember k plus r has to equal n, that means our r value has to be 4. Okay, so once we've identified all 5 of our variables, then it's a matter of just plugging it into the calculator and running it through. Okay, so let me switch to a color I haven't used. We'll work with the lovely brown color. So the probability that 3 survive, or we could say, survive, or we could say 3 successes or 3 recover, or whatever you want to call it, is equal to, and we're going to go back to our formula here, NCK. So our n value is 7. CK, which is 3, times, we got p to the k power. P is 0.8, so 0.8 to the k power, which is, again, 3, times, what do we got left? Q to the r power. So Q is 0.2, and our r value here is 4. Now, you can type this in exactly like that in the calculator and get an answer. If you want to do it individually, you can do that too. I'll do it individually just so you can see where some of these numbers are coming from. 7C3 in the calculator is 35. 0.8 to the third power is going to be 0.512, and then 0.2 to the fourth power is going to be 0.0016, and then we can multiply all those 3 together, and we get 0.02867. Now that's the decimal in the probability. The probability is a decimal. If you want to write it as a percent, feel free. We can say it is about 2.9%, because remember we'd have to move this decimal point 1, 2 to the left. 2.8672, we can call that 2.9%. So our answer here, the probability that exactly 3 people survive is about 2.9%. Now, the reason it's so low is because if our probability of survival is 80%, it's more than likely going to be that more than 3 people survive. And we can kind of decide which one or which outcome is most likely if we're given something like this type of problem. And that's what we're going to do here in this second question. A landscaping company knows that any tree they plant has a survival rate of 70% if cared for properly. If the company plants 7 trees, how many trees are most likely to survive? Okay, we're actually going to do a lot of work, or at least a lot of writing in this specific problem. We're not being asked for a specific outcome. It's not what's the probability that 2 trees survive, or what's the probability that 5 trees survive. We need to figure out which one is most likely. So what I'm going to do, I'm going to write a little note here. We need to find all possible outcomes, or find all probabilities. Okay, so all the possible outcomes, or all the probabilities, we're planting 7 trees. So there are actually 8 outcomes here. We could find the probability that 0 survive. We need to find the probability that 1 survives. We need to find the probability that 2 survive. The probability that 3 survive. I'm going to have to move this up. Probability that 4, 5, 6, or even 7, all 7 trees survive. Okay? And I'm just going to kind of put equals, leave that gap, because I just don't want to write it all. And this way I can kind of keep everything lined up. Okay, before we can figure out each probability, we might need to know some values here. We know that 70%, that's the survival rate, so that is our probability of success. So we can say our p-value is 0.7. Remember, probabilities need to be in decimal form when we're writing, putting them in the formula. If our probability of success is 70%, our probability of failure is going to be 30%, or 0.3. Okay, and then the last thing that we're told in this problem is the number of trials. Okay, the n value here is 7. Okay, what we're doing down here with all this information, we're deciding our specific k value. In this one, k is 0, 1, 2, all the way down to 7. Okay, and if our k is 0, that means our r value is 7. So what we're going to do, we're going to be writing a lot with this problem. So I'm just going to kind of go down the line with each problem and just kind of work it through. So our first number is going to be 7 for every one of these. 7, it's going to be 7c something, 7c something, 7c, 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 7c. Now, this is where things start to change. So this number right here, our k value, is going to go right here. So this case, it's going to be 7c0, 7c1, 2, 3, 4, 5, 6, 7, and then we'll go back to some uniformity. Then it's going to be times the probability of success, which is 0.7. So 0.7, 0.7, 0.7, all the way down the line. Let's see, I'll screw that up. 0.7, 0.7, 0.7, and one more 0.7. Now, these problems take a while. I'm not going to give you many of these, but just so you understand how it's possible to do this. Remember this number down here, the number after the C is the exponent, the number of successes. So this is going to be 0, 1, 2, 3, 4, 5, 6, and 7. So there's our probability of success. Now we need to account for our probability of failure. So 0.3, 0.3. The probability of failure is going to be the same value for every one of them. That's what makes it a binomial experiment. 0.3, 0.3, 0.3, and 0.3. And remember, the K value and the R value need to add up to N. So this is going to go from 7 all the way down to 0. 7, 6, 5, 4, 3, 2, 1, and 0. So now we've got all the formulas filled in. Now it's just a matter of typing it in the calculator. What I'm going to do as I'm making this video, I'm going to pause it just because we don't need to spend time watching me write. I'm going to pause it and I'm going to fill in the probabilities, the individual probabilities, and then we'll talk about what the answers mean here in just a second. All right, so I've got all 8 probabilities here, going from very, very small to fairly large and then coming back down. So the question was, how many trees are most likely to survive? Well, which of these 8 probabilities is the greatest? Well, to me, it looks like this one. It would be 5 because that one's got the highest probability. Now, in theory, if we added these numbers together, we should get a grand total of 1, and I haven't done that, so I don't know. It might actually end up being 1. It might be really, really close. It's kind of a rounding issue, but I gave as many decimals as what my calculator would give me. Feel free to not do that. If you want to, let's say with this one, if you want to go like 0.318, I'm fine with that. Like I said, I just gave you all the decimals that were on my calculator, but what we're looking for here is the biggest one. Which one is most likely? Well, which one has the highest probability? In this case, it is 5. So the answer to the actual question, how many trees are most likely to survive, we could say 5 trees. That would be our answer there for question number 2. All right, the last one here, about 70%, and again, I'm using 70, that's just kind of how the question happened. About 70% of the questions created by a random computer test generator for a science test are multiple choice. The rest of the questions are true, false, or matching. What is the probability that at least 3 of the 5 questions generated for a short quiz are multiple choice? So the key here, this phrase right here, at least 3, and this goes back to section 4 when we're talking inclusive and exclusive events. We can't have 3 and 4. It's either 3 or 4 or 5. So at least 3, I'm going to write this again off to the side here. So at least 3 means 3 or 4 or 5, because we're talking 5 questions, okay? So what we need to do is we need to find the probability that we get 3, probability that we get exactly 4, probability that we get exactly 5, and then add them together, and that will give us our final answer. Now, we do have 3 outcomes here, and the difference or the issue with this is if we go back to our qualifications, it says exactly 2 outcomes. And if we look at this, we've got multiple choice, true, false, or matching. Now, I can say, I would argue that we could lump this, we could make this into 2 separate possible outcomes. We can call this multiple choice, and we can call it not multiple choice. So we can make this a binomial experiment if we group true, false, and matching together, because it's not multiple choice. Okay, so we can still do this. Let's identify our n value. How many questions are we having on this quiz? We have 5, so our n value is 5. The probability that we get a multiple choice question, says it right there at the beginning, 70%. So 70% as a decimal is 0.7, which means the probability that we don't get a multiple choice is going to be 0.3. 70 plus 30 is 100%. And then we need to go from there. We'll need to write out our 3 possible solutions, our 3 possible outcomes. We need to find the probability that we get 3 multiple choice. We need to find the probability that we get 4 multiple choice, and we need to find the probability that we get 5 multiple choice, and then we're going to add these together. So for 3 multiple choice, we have 5. We need to choose 3 of our questions to be multiple choice, times the probability that we get a success, which is a multiple choice question, 0.7, and we need 3 of those, times the probability that we don't get a multiple choice, which is 0.3, and we need 2 of those. We're going to do the same thing with 4 and 5. So we're going to have 5C4 this time because we need 4 of our 5 questions to be multiple choice. It doesn't matter what order they're in as long as 5 or 4 of the 5 are multiple choice. Times 0.7, can probability we get a multiple choice to the 4th power because we got 4 of them, and 0.3 to the 1st power. And then same thing with 5 questions, 5C5 times 0.7 to the 5th power times 0.3 to the 0 power. Now we're just going to type these in our calculator. I've already done that. It's going to be 0.3087 for 3 questions, 0.36015 for 4 questions, and for 5 multiple choice questions, it's going to be 0.16807. What we're going to do with those 3, since we're talking about at least 3, we can't have 3 and 4 and 5. We can only have 1 at a time, which makes these exclusive events, which means we're going to add them together. At least 3 is going to be equal to our 3 probabilities added together. So 0.3087 plus 0.36015 plus 0.16807, which is equal to 0.83622. So decimal form, there's our answer. If you want to write it as a percent, we could say it's about 84%. So about an 84% chance that we'll have at least 3 multiple choice questions on this quiz.